Hello. Today we are going to discuss about plasmons. So we all know about the quantization of energy. The quantized form of electromagnetic energy is called photon. Just like that, the quantized form of plasma oscillations, which are called plasmons. So in a crystal, we know that there are atoms. There is a kind of lattice points around which the group of atoms will be attached to that particular lattice points, and each atom will be having many electrons, the outermost electrons, and we can see that there are many surface electrons. So these electrons, when we excite light onto this kind of group of atoms with electrons, surface electrons, these electrons will oscillate. This light can also, because light is a wave, right? It is we are importing some light, we are transmitting some light to these electrons, and these electrons, that is transfer of energy. Because of this wave, there will be an oscillations. So these electrons will oscillate, and the nucleus of the atom will try to pull back the electrons. So that means there is a kind of oscillations, and these type of oscillations are called plasma oscillations, and the quantized form of that oscillations, that is the minimum quantized form of that plasma oscillation, is called the plasmons. So the plasma, which is we normally consider as an ionized gas, so it is a kind of ionized electron gas. And before discussing about the plasmons and plasma optics, so the plasma optics deal with how light can this plasmon will manipulate the light. So that is the interaction of light into these plasmons. So how there will be some different kind of behavior of light in plasmons. So that is what is called the plasma optics. So before going to the details, we need to discuss about the dielectric functions. So the dielectric function, we can consider two limits. So which is a function of both frequency and wave vector. The dielectric function is a function of both frequency and wave vector. And in this limit, when k is equal to 0, and when that is the wavelength dependent dielectric functions, which corresponds to the describe the surface plasmon, the plasma oscillations. And in this limit, when omega tends to 0, that is E0k, when it is only a factor of k, which describe the lattice electrostatic interaction between these electrons and lattice, or otherwise the electron-electron interaction. Such electrostatic screening will be we need to consider E0k. We will consider about this one first. So for that, in order to consider the wavelength dependent dielectric functions, we need to discuss about the equation of motion. In order to get that value, we can consider the equation of motion of free electron. So we consider an electron which is moving under influence of an electric field, and the corresponding equation of motion is this one, Ma is equal to minus EE, the charge into electric field. So this is m d square x by dt square is equal to minus E into E. Now let's consider that both this displacement, the displacement of these electrons as well as the electric field is a function of temperature. It's a oscillating function. So it is a function of time, that is E proportional to e raised to minus I omega t. So it's a wave depending on time. So both these terms will be depending on time like this. So if we substitute these values here, we can get this one, m d square by dt square of e raised to minus I omega t is equal to minus E into E. Now on taking second derivative of this one, we will get this value, that is minus m omega square into e raised to minus omega t is equal to minus E into E. And that is, we can consider in this form, that is minus m omega square x is equal to minus E into E, so that we can write the expression for displacement is equal to E into E divided by m omega square. Now the dipole moment of the electron, so that is the charge into distance, the charge into displacement happens to the electron, that is this one, and the polarization is the dipole moment per unit volume. So that is minus n. We just multiply this dipole moment with n, where n is the electron concentrations. So that is minus Ne we substitute for x here. So you get this expression that is equal to this one. So the polarization is equal to minus ne square E by m omega square. Now the dielectric functions. So we are going to derive the value for the dielectric function, that is depending on displacement vector like this, d is equal to epsilon E, and then we can get the value of epsilon omega, that is d omega by e omega. So this is equal to, the displacement vector is equal to E plus 4 pi p divided by E. So this is in CGS unit. The displacement vector expressed in CGS unit, and this is equal to 1 plus 4 pi p by E. So this is the dielectric function of free electron gas. Now we substitute for P from equation number 3. You will get this expression, that is epsilon omega is equal to 1 minus 4 pi ne square by m omega square, that is equal to, we can write 1 minus omega p square by omega square, where this omega p is defined as omega p square is defined as 4 pi ne square by m. So that is the we define this omega p as the plasma frequency. We just observed how the dielectric function epsilon omega depending on the frequency. So this was the expression epsilon omega is equal to 1 minus omega square divided by omega p square. So we, in order to derive this, we consider the free electron equation of motion of electron in a electric field. So we just consider the electrons as a free electrons. But in a plasma medium, there will be an equal number of equal distribution of positive and negative charges. So these negative charges are due to the displaced electrons. So electrons will be displaced when we apply the electric field. So that is that contribute the negative charges, whereas the ion core, so the ion core of the atoms, the positive ion core, that will contribute the positive charge distribution in a plasma. So there will be an equal number of positive and negative charges inside a plasma medium. So we need to consider that. So we need to consider the dielectric functions, which is the of the ionic background. So electrons are displaced in a ionic background medium, and the corresponding dielectric functions, that is defined as the epsilon infinity, which is due to the ion core background, and which is also called the optical dielectric constants. So now the epsilon omega can be expressed as is equal to epsilon infinity minus 4 pi ne square divided by m omega square. Now we take this one outside, so that this epsilon infinity into 1 minus 4 pi ne square divided by m omega square into epsilon infinity, and we can simplify this equation into this form, epsilon infinity into 1 minus omega p caps square divided by omega square, where this omega p cap which is related as this square is equal to 4 pi ne square divided by m epsilon infinity. So this is the actual plasma frequency, and from this expression we can see that when omega is equal to omega p, this terms will be 0. So this the right, so that is the dielectric constant, the dielectric function becomes 0 when omega is equal to omega p at plasma frequency. Now we can see that when when epsilon is positive, that is this omega p is less than omega. When this plasma frequency value is less than omega, this will be a positive quantity, and so that is a real electromagnetic wave. So in this type of medium, when epsilon is a positive, this corresponds to the real electromagnetic wave which will be propagating. So we can see that only when omega is less than omega p is less than omega, this will be the dielectric function will be a positive quantity. Correspondingly, that is corresponds to propagating medium. So that is the region of propagation. This corresponds to the region of propagations, and when we can see that when omega p is greater than omega, when omega p is greater than omega, this will be a negative quantity. So that corresponds to in that particular medium, the electromagnetic wave will be reflected back. So there are actually we can draw the function of the epsilon omega, the dielectric function as a function of frequency. So this is the particular structure, the graph which shows the variation of epsilon omega with frequency. Actually the omega by omega p. We consider the omega by omega p. So there are different scales here. You can see that at omega by omega is equal to omega p, this epsilon is equal to 0. And we can see that when it is omega by omega p is less than 1, that corresponds to the negative. The epsilon value will be negative quantity, and it is called the region of attenuation. So when the electromagnetic wave is passing through this medium, that is epsilon negative medium, so we can see that this will be attenuated. So the electromagnetic wave will be reflected back. So when omega is, this one is a positive, that is called the region of propagations, where we can see that this will be a real quantity and it is corresponds to the propagating. So actually when an electromagnetic wave with frequency omega p, when it is incident on a plasma medium, and when the frequency is less than corresponding omega p, the plasma frequency, that corresponds to the region of attenuations where the wave will be reflected back. Whereas when the frequency is greater than this corresponding plasma frequency, it will be propagated. So it will be propagated corresponds to that when it is above plasma frequency. So from this we can see that the electromagnetic wave in a plasma medium will behave differently. So when only when the frequency of the electromagnetic wave is greater than corresponding plasma frequency, it will be propagated through the medium. So we'll conclude here. Thank you.